Okay, good morning. Today is the last day we want to talk about combinatorics, and that is a very famous theorem. It's called the binomial theorem. The concept is very simple, but it's of practical use. For example, if I have a polynomial with two terms, I call it a binomial. For example, if A and B are added, this is a binomial. Now, what is binomial theorem? It tells you how to expand this binomial if you raise it to high powers, natural powers, of course. Now, of course, for case 1, it is already trivial. For case 2, for the case that the exponent is 2, this is a very famous identity. The first one squared, 2 times the first one times the second one, plus the second one squared. And I don't know, sometimes you might see this in the formula sheet as well. This becomes the first one cubed, 3 times the first one squared times the second one, plus 3 times the first one times the second one squared, plus the second one cubed. But the question is that what happens if I increase the exponent? So for example, what will happen if I have a to the power of 4, if I have a plus b to the power of 5? So whenever I have a binomial, I want to raise it to a natural power without writing any pairs of brackets. That's the expansion. What do you expect? What terms do you expect here in front? And in principle, this is the question. A and B are real numbers. N is a natural number. Then the question is that what can I write for a plus b to power n? This is what we want to answer now. Okay. So one way is have the formula and use mathematical induction on n to prove it. It's a good exercise in mathematical induction. I don't know if you have time. We can also go through it a little bit. But the weakness of induction is always as usual. So you need to have the full formula and then you're able to prove it. Yeah, might be by checking some special cases, you can discover a pattern, and then that pattern is the formula that you expect, then you prove it by mathematical induction. So it is not that powerful. I hope that you agree with me, yes? But now we want to use the idea of combinatorics, counting, to find the formula, which is an algebraic formula. In principle, this formula shouldn't depend on combinatorics. But combinatorics, this is a very good example to show that combinatorics is not just for counting things, but sometimes it is possible to use the ideas of combinatorics to develop algebraic identities as well. Okay, let us try to understand this from a combinatorial point of view. So let us start. This is a very trivial case, so let us forget about that. But let me start from a plus b to power 2. So a plus b to power 2 means what? Means a plus b multiplied by a plus b. If I want to multiply this pair of brackets by the other pair of brackets, I have to consider all possible products. Okay? So what are the possible products? One possibility is that I take a from the first pair and I take a from the second pair and it gives me a squared. Okay? So it means that I have to have two a's. A times a is one possibility. But you know what happens for the next one. By the way, how many of these possibilities you expect? How many a times a's you will expect? Yes, one. Because a, I have two pairs of brackets. If I want to generate a by a, I have to choose a from this, and I have to choose a from that. And I can choose it in one way, I can choose it in one way, so there is only one way to have a times a. Okay? But now let us see that I want to have a times b. So a times b, in how many ways do you think a times b occur? Yes? Two ways. Either I choose a from the first pair and b from the second pair, it gives rise to ab, or I choose a b from the first pair and a from the second pair, it gives me a BA, but BA and AB in algebra are the same, so that is why I will have two of them. Yes? So I will have two of them here. This means that I have only one of them. I will have two of them. And then what is the other scenario is that I choose B from here, I choose B from there, and it gives me B times B. And how many ways I can construct B times B? Only one way. Okay, so that is the reason. This is a good way because now by understanding this, you can generalize the idea and finally you can get this formula right. So this means that this is a squared plus 2ab plus b squared. Okay, so let us understand a plus b to power 3 as well. So I have a plus b multiplied by itself 3 times. So because I have 3 pairs of brackets, and each pair of within each pair of bracket I have 2 options. Either I choose A or I choose B. Yes? So, for example, if I want to generate, is it possible to generate A times A times A? Yes. And that is when I choose A from here, A from there, A from there. Okay, so it means that my products have 3 factors within them. Yes, this is one possible product that I will get out of when multiplying things. And that is that is for the case when I am choosing A from here, A from here, A from there. But is it possible that I have 2 A's and 1 B? Yes, that's correct. That's possible because I choose 2 A's and 1 B. But the problem is that in how many ways I can choose 2 A's and 1 B? Yes, that is 3. Because either I choose A from here, A from here, B from there, or I can choose A from here, B from here, and A from there, or I can choose B from here, A from here, A from there. So if I want to have 2 A's chosen and 1 B chosen, I have 3 options available. Yes? And the good news is that the product here generates what? A squared B. The product here generates the same. The product here generates the same. So if I am patient and start multiplying things one by one, definitely I will get this term 3 times. Yes? So that is why, if I want to understand it, a times a times a, which is a cubed, appears 1 in one way, but a squared b appears in 3 different ways, but when I add them up, all of them will be this one. And I hope that you agree that the other opportunity is that I have 1a and 2 b's, yes? In how many ways I can choose 1a and 2 b's? Again, 3, yes? A, B, B, A, B, A, B, and B, B, A. But this will give rise to AB squared. This will also give rise to AB squared. This will also give rise to AB squared. So when I add them up, it means that when I expand, there will be 3 AB squareds involved. So I will add them up, so it becomes 3AB squared again. And then finally for B cubed, how many possibilities are there? There's only one possibility. I have to choose B from here, B from there, so it becomes 1B. So then it means that if I expand that, I should expect this. And of course, I don't need to write the ones. And that is the answer to this problem, yes? Let us try to go one step forward and then try to find this answer using this idea. And then we generalize and find the pattern. So for a plus b to the power of 4, it becomes a plus b, a plus b, a plus b, and a plus b. Yes? So you can imagine that you are supposed to expand this. So in how many ways, how many different combinations I have? Either I choose 4 A's, or I choose 3 A's, or I choose 2 A's, or I choose 1 A, or I choose no A's. Yes? These are the only possible ways if I want to choose A. Of course, when I say choose 4A, it means no B's are left. When I say choose 3 A's, in principle, I have to choose 4 items, but 3 of them is A, it means the leftover should be a B. Yes, is that understandable what I'm writing? So if you want, let me write it in this way. Yes, so for A, either I choose 4 times, it means that I choose A from here, A from here, A from here, A from here. But sometimes I prefer to choose 3 A's. I have 4 boxes. In each box I have 1 A, 1 B. Here I decide to choose 3 of them and choose A from it. It means the leftover should be B. Or I choose 2 A's, 2 B's. I choose 1 A, 3 B's. I choose no A's and 4 B's. These are all possible options. Yes? So this one will give me which type of term? It gives me a to the power of 4. This one will give me a to power 3b. This one will give me a squared b squared. This will give me a b cubed, and this will give me b to the power of 4. But I want to know how many of each one of them I have. Yes? So these are only terms that are involved. So you already know the answer to some extent. So you know that there should be a 4 involved. You know that there should be a cubed b squared b involved, a squared b squared involved, a b cubed involved, and finally b to the power of 4 involved. So the only problem is that how many of each one of them I will have if I am patient and expand this fully. Okay, this one is easy to guess. What is that? It's 1. When you say 4 A's and I have 4 boxes and I want to choose 4 A's, it means from this box I choose A. That's one option, yes? Okay, so that is 1. But what about this one? That is 4, yes? That is 4. Okay, what about this one? That's the whole point. I don't want you to imagine. I want you to use the methods we have developed in combinatorics so far to answer that question. So for example, A4 can be viewed in this way. Okay. So in how many ways I can arrange these items in a row? 1. In other words, I have 4 factorial, but 4 of them are repeated, so I divide by 4 factorial. So this means that this is 1. Yes? But if I have 3 A's and B, so in this order, it means I am choosing A from here, from here, from there, and B from there. But in how many ways I can arrange them in a row? It's 4 factorial again, but by divided by, this is repeated 3 times. If you don't mind, let me also emphasize this is repeated 1 time. It doesn't matter, of course. And that if you calculate this number, it is 4 factorial divided by 3 factorial, which is 4. And that is the reason that you answered that this is 4. Okay? And then let us go to the next one. Here I have 2 A's and 2 B's. In this order, it means I chose A from here, B from here, B from there. But I can choose it in a different way, yes? I can write A, B. What does this order mean? It means from first I chose A, from the second I chose B, from the third I chose A, from the fourth I chose B. So if I consider all possible scenarios here, how should I count them? 4 factorial, but 2 factorial because of 2 times repetition of A, and 2 factorial because of 2 times repetition of B. So that number, as you said, if you calculate that, it becomes 6. Yes? And now, do I need to calculate this again? This time, I have 1 A and 3 B's. Yes? But of course, hopefully you understand, if you change the labels A to B's and B's to A, you will have this scenario again. So, but again, if you want, you can say that 4 factorial divided by 1 factorial, 3 factorial. So what is the number here? Is 4. Yes? And then finally the last one is for the same reason, b, 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 b. So it becomes 4 factorial divided by 4 factorial. So it is 1a. Yes? Okay, so what we do, we can say that a plus b to the power of 4 is equal to. Here, I want to write the coefficients in a little bit different way. Do you remember this formula? We had n choose r is equal to n factorial divided by r factorial, the difference between them factorial. Yes? Okay, can you write this here? If you don't mind, here, I want to add a 0 factorial here as well. I want to add a 0 factorial here, there as well. Because the reason I am doing it, because I want to see the pattern. Yes? So the numerator is always 4 factorial. But what can happen for the denominator? I have 4 and 0. I have 3 and 1. I have 2 and 2. I have 1 and 3. I have 0 and 4. Those numbers are exactly these numbers that you see here. Okay? So, but I can write all of them as a combination for number. So, what is the first one? The first one is 4 choose 0. Do you agree? Because it becomes 4 factorial, 0 factorial, the difference between them 4 factorial. And that is a to the power of 4. The next one is of course a to the power of 3b. But what is the coefficient? The coefficient is on the board. Can I write it as 4 choose 1? Yes. Why? Because it becomes 4 factorial. This one, 1 factorial. The difference between them, 3 factorial. That's also correct. So then what happens for the next? I will have a squared, b squared. But can I write it as 4 choose 2? Yes. Because 4 factorial. The difference, so this 2 factorial and the difference between them again 2 factorial. That's correct. And then I continue this. It becomes 4, 3, ab cubed, and then finally 4, 4, b4. So this is the reason, because they appear in the binomial expansion, if you see them, these are called binomial coefficients. This is another name for this, binomial coefficients. So for example, in LaTeX, if you want to type this, it is binom, \binom, curly brackets, and curly brackets r, if I'm right. But I'm sure about this term. That's \binom, and that's the reason. Yes, is that right? So this is the binomial theorem for the special case that n is 4. Yes? But I hope that you agree with me, I can do the same analysis for the power of n, because this goes exactly like that, yes? So can we predict what will happen if I have a plus b to the power of n? So what are the terms, what are the possible cases? Either how many a's I can have at most, n, no b's, and then n minus 1a, 1b, n minus 2a, 2b's, and then it continues, I don't know, let us say 2 a's and n minus 2b's, and then 1a and n minus 1b, and finally no a's, all of them b's. Yes? This will give rise to what? This will give me a to the power of n, b to power 0. This will give me what? A to the power of 1 unit less with 1b. This will give me a to the power of n minus 2 with 2b's. And then finally, it will give me 2a's with n minus 2b's. This will give me 1a, which I can write simply a, b to the power of n minus 1. And this will give me no a's, but all of them b's. So this is clear that this will happen, but then I want to calculate the coefficients. So what are the coefficients? So this becomes an, the coefficient an, the coefficient is what? N choose 0. The next one is I have n factorial because I have n items, but n minus 1 of them is of the first type. So I put an n minus 1 factorial and one of them is of the other type. But this can be written simply as n choose 1 a to power n minus 1 b. Yes. The next one, I have n items again, but n minus 2 of them of one type, 2 of them are of the other type. So the answer will be n factorial and then n minus 2 factorial, 2 factorial. So the next one becomes n choose 2 a to the power of n minus 2 b to the power of 2. Do you agree? This number is n choose 2. N factorial, 2 factorial, the difference between them factorial. And then this list will continue, yes? So n choose 3. So let me just follow exactly those things that I have written. So some dots, and then the last 3 terms, for example, n choose n minus 2, a to the power of 2, b to the power of n minus 2, and then n choose n minus 1, a to the power of 1, b to the power of n minus 1, and finally n choose n, bn. So that formula that you see here is called Newton's, sometimes they say, Newton's binomial theorem. And because that's a long formula, but you see the pattern whenever you have a long sum, so that the patterns of the terms are following a particular pattern, you probably can put it in sigma form. Yes, so that is better. So for a sigma, because that is a sum, you suspect that you might be able to write it as a sigma. Sigma needs a counter, so let me choose the letter K for the counter. And then I have to write something in the front of the sigma, and I have to assign a limit, a lower limit for K, an upper limit for K, so that when I replace the K in that expression with those values, I generate these terms one by one. So what do you think the pattern is? You see, all of them has a combination number here. So what is the pattern for the combination numbers? The top number is always n. So the top number is always n. The lower number is the number that is changing. It starts from 0, goes one step at a time until it reaches to n. Okay, so what do you think is good to put here? K. And K goes from where to where? The starting value is 0, the highest value is n. And then what should I write here? You see, this is power n, then it becomes n minus 1, then it becomes n minus 2. It continues to a and nothing. So what do you think I will write here? I need to write 1a, I need to write 1b. What should I put as the exponent for a and the exponent for b? N minus k for a and k for b. Yes? So that is the formula that I will write and keep it so that we can solve some problems, okay? So if a and b are real numbers, and n is an integer, then a plus b to the power of n is sigma. K goes from 0 to n choose k, a to power n minus k, b to power k. So be careful. This n, that n, this n, and that n are all the same. Newton's binomial theorem, this is the claim, and then hopefully you agree with you're convinced with the proof, combinatorial proof. But now that you have the formula in its full form, if you insist, you can use mathematical induction to prove that's true. It's a very good exercise in mathematical induction itself. Is that clear? Okay. So, for example, there are some questions in the book. They ask you to expand. For example, let us say I want to expand 2x minus 3y to the power of 5. Yes? I want to expand this expression. Is this formula relevant in this case? I would say yes, because that's a binomial expression, and I want to raise it to a natural number. I want to raise it to a natural number. So it is relevant. But of course, here you have to adjust yourself with that formula. So in the formula, I will replace a with 2x. I will replace b with minus 3y. And I replace n with 5. Yes? Okay, and then I put it in the formula. So some problems are boring. There are exercises of this type, so you should be able to use this formula and open it up. So what happens here? This becomes sigma. K goes from 0 to which number here? N. N is 5. And then I put 5n, choose k. A, which is 2x in this case, to the power of n minus k, but n is 5, so it becomes 5 minus k. And then the second one is minus 3y to the power of k. And then this is just a boring exercise. You have to open up the sigma, calculate the coefficients, and simplify as much as I can. Of course, might be you need calculator, but let us see how it goes. So the first thing, I put 0. So it becomes 5 choose 0, 2x to the power of 5. That's it. Because if you put 0 here, it becomes 1. The next one is plus 5 choose 1. And then I have 2x to the power of 5 minus 1, which is 4, multiplied by minus 3y to the power of 1. The next one, 5 choose 2. And then you have 2x to the power of 3, but minus 3y to the power of 2. And then the next one, 5 choose 3. You have 2x to the power of 2, minus 3y to the power of 3. And then 5 choose 4. 2x to the power of 1, minus 3y to the power of what? 4. And finally, 5 choose 5. No 2x. Minus 3y to the power of 5. Yes? Okay, so we have to calculate if you want to finalize everything. But do you remember what is 5n choose 0 for any n? It is 1. And then 2x to power 5 becomes 32x to the power of 5. So what is 5 choose 1? I have 5 students, I want to choose one of them, so it's 5. So it's 5. And there is a 16 coming out from here, times that 5 is 80, and there is a minus 3 here. It's minus 240 x to the power of 4y. Yes? So this number is 5, 2 to power 4 is 16, minus 3 to power 4 is minus 3. So if you multiply them, it becomes 240, minus 240. And then I have the fourth power of x, first power of y. Okay, so if you are patient and calculate this, I know that this becomes 10. Okay, and then 2 to power 3 is 8, minus 3 to power 2 is 9. So it becomes 720. So it becomes plus 720 x to power 3, y to power 2. And then, do I need to calculate these things? Because 5, 3 is a very famous identity. You see, this one and the last one are equal. This one and that one are equal. And this one and that one are equal, because 3 plus 2 becomes 5. So if this is 10, you don't have to calculate this one. That's also 10 again, but I have a 4 here and a minus 27 from here. So what's the answer? Minus 1080, and then I have x to the power of 2, y cubed. Yes? And then again, what is 5 choose 4? 5 choose 4 is the same as 5 choose 1. So if that was 5, that also becomes 5. But this time this becomes 2, and then this becomes what? 81. It's very simple, so we were lucky. This becomes plus 810 x y to the power of 4. Yes? And then finally, this is just 1, and this is minus 243. So it is just minus 243 y to the power of 5. Of course, it might be lengthy, but if you want to multiply it 5 times, it includes 32 terms. And then you have to keep track of all similar terms and things like that. So that's the expansion of this. It's a boring part, but necessary to know. Any questions so far? But I also have something in mind. I can do it faster. I will tell you, but you don't have to learn it if you don't like it. But what I will do, this is not hard to prove that it works. So, for example, let us start with just a very simple one. So, for example, a plus b to the power of 7. Okay. So what I do, of course, I can prove it using the formula, but let me tell you what to do. I will raise it to the power of 7 first. And then for the next one, I know what is the term. The term is a6b, yes? I have to reduce 1 from here and add 1 power to b. The problem is that what the coefficient is. Of course, the coefficient is also simple in this case. It becomes what? 7 choose 1. But the method that I use, I take the power of a, multiply it by this coefficient. It becomes what? 7. And then I say that how many terms I have written so far? 1 term. So 7 divided by 1 is 7. Okay? And then when I go to the next one, I multiply the power by here, which becomes 42. How many terms I have written so far? 2. 42 divided by 2 is 21. Yes? And for example, for the next one, I have to convince you that this method works, but that's not very hard. Okay? So what is the next one? If you learned what I said. So you know that the term is what? A4B3. This is clear. But the coefficient matters. So what's the coefficient? You go to the previous term. You multiply this power by this. It becomes 105. And then you divide it by 1, 2, 3, which is 35. Yes? And then, by the way, how many terms are there? Can you tell me how many terms are there when I expand? Not n. Because k starts from 0 to n. So there is n plus 1 term. Yes? So this is also good to know. In the expansion, you have n plus 1 terms. Because if k goes from 1 to n, you have exactly n terms. But now k goes from 0 to n, so you have n plus 1 terms. So how many terms you expect here? 8 terms. So 1, 2, 3, 4. And then the rest of it is the same. Of course, you can follow the same rule, but no one will do that because I will have a B7 here. What is the coefficient of B7? It should be 1. The previous one is what? A6B. Yes? So sorry, AB6. But the coefficient of AB6 and A6B are the same. So if this is 7, that one is also 7. The previous one is what? A2B5. Yes? So what is the coefficient? 21. Yes? 21. And there is one more here. What is that? A3b, A3b, 4. What is the coefficient? 35. So that's one way to do it faster. Of course, you could continue the same way. For example, if I want to find this, I multiply 4 by 35, and then I ask myself how many terms I have written so far. 4 terms. The answer becomes 35. So why do you think this is correct? Why this idea is correct? We have to go and find a formula, okay? So, for example, what is my claim? My claim is the coefficient of the kth term. This is the claim, yes? Because at any point, if I want to find this coefficient, let us say this is the kth term, I am claiming that the coefficient of the kth term is equal to the coefficient of what? The term k minus 1, yes, multiplied by what? Multiplied by the exponent of a in the previous term, k minus 1, term k minus 1, yes, divided by, can you tell me divided by what? Written before that, yes? So if I am interested in the 4th term, I have to divide by 3. If I am interested in the 5th term, I have to divide by 4. So I have to divide by k minus 1. So this is the claim that I am using it. I am saying that the coefficient of the kth term is equal to the coefficient of the term k minus 1 multiplied by the exponent of a in term k minus 1 divided by k minus 1. But how should we prove this? Okay, look at the formula. Okay, can you tell me what is the coefficient of term k minus 1? This is the coefficient of which term? Can you tell me? And choose k is the coefficient of which term? No, because it starts from 0, so don't get confused. Yes? No, there's no term minus 1, yes. So you see, if I put 0, n0 is the coefficient of the first term. When I put 1, this is the coefficient of the second term. So the term number is 1 more than this number in the bottom. Okay, so when I say the coefficient of the, so let me write from the right hand side. So right hand side is 1 over k minus 1 multiplied by. Okay, so can you tell me what is this one now? It is n choose what? The coefficient of the term k minus 1. K minus 2. N choose k minus 2. Is that right? Because, for example, if I say, tell me the coefficient of the first term, you put 0 here. If I tell you, give me the coefficient of the second term, you put 1 here. If I tell you, give me the coefficient of the third term, you put 2 here. If I ask you, give me the coefficient of term k minus 1, what do you put here? K minus 2. So that's it. Okay? Multiplied by the exponent of a in term k minus 1. So what is the exponent of a in term k minus 1? So the coefficient, the power of n, so this is n minus k. Okay, so when I put 0, a to power n is the first one. The second one is n minus 1. The third one is n minus 2. So the k minus 1 is what? A to power n minus. It is not hard, is it? No, not k. So you see, the first term, it is n minus 0. The second term is n minus 1. The third term is n minus 2. So yes, you said what? No, k you said. Yeah, that's correct. It's n minus k. Yes? Because you know, no. Yeah, this is something like this. K minus 2. Yes? Because you see, if this number is 1, this number is 1 unit less. If this number is 2, this number is 1 unit less. If this is 3, this is 1 unit less. Now this is k minus 1. So 1 unit less becomes k minus 2. So I have to write n minus k minus 2. Yes? Yeah.
When you write the k term there, do you refer to k as in the zero-based, the k that starts from 0, or the, I don't know, index that starts at 1?
No. I am assuming exactly like what I have done here on the board. So I consider this the first term, the second term, the third term. Let us say this is the kth term.
Okay, so the k in the sentence k term is equal to k in the formula plus 1.
Plus 1.
Okay, why don't you use the same thing? Okay, sure.
No, because this doesn't make sense. You see, when I write this, forget about the formula. If I ask you which term is that, you will tell me term number 1, 2, 3, 4. No, I mean this is the natural way of calling. If I write this for you and I say which one is which term is that, you will tell me the fourth term. Yes, but the fourth term, that's what I'm saying. So if you want n, choose k, a to the power of n minus k, b to the power k is the k plus first term.
Sure, it would be nicer to just count from 0, especially in this formula. So the 0th term and first term and whatever, but I guess that's...
No, because for me natural is that if I write this and I ask you which term is that, you don't tell me this is term number 3. You will tell me this is term number 4. So in that regard, it's natural to call it term number 4. But if I want to keep the consistency, not to be confused, then I can start numbering them from 0. Yes. Anyway, but then you have to multiply it by what? Finally, can you tell me? N minus k minus 2 is n minus k plus 2. If I simplify this, I should get the coefficient of the kth term. If I can prove this one for you, then probably we are done. And I think we can do it, yes? Because this becomes 1 over k minus 1 multiplied. For this one, I have n factorial, I have k minus 2 factorial, and then I have the difference between them, which is luckily exactly this expression factorial. And then you have n minus k plus 2 there as well. Okay, now can I simplify this a little bit more? N factorial is n factorial. But then this one and that one can be combined to what? K minus 1 times k minus 2 factorial. So it becomes k minus 1 factorial. And n minus k plus 2 factorial can be written as n minus k plus 2 times the previous factorial. But n minus k plus 2 will cancel that one, so I will be left with n minus k plus 1 factorial. Yes? But this can be simply written as n choose k minus 1. And that is the coefficient of the kth term. So the coefficient of the kth term, which is this one, is equal to the coefficient of the term k minus 1, the previous term, multiplied by the exponent of a in the previous term, divided by the term number of the previous term. So anyway, You can write it in your own way. But this is a very efficient way, even though you have to memorize this, but it's much faster than to write all the combinatorial numbers and then calculate them and etc. For example, let me just immediately do the next one and then we move on. Okay, so what we want to do now, for example, can you write this a plus b to power 8 fast, okay? So what we write a to the 8th. What is the next term? Is a7b. But what is the coefficient? 8 multiplied by 1 is 8 divided by 1 term is 8. What is the next one? 7 times 8 divided by 2, which becomes 28. Yes? The next one is what? Can you see that in your head? 6, you don't need to multiply. 628 divided by 3. So this becomes 256. 56, a to power 5, b to power 3. What is the next one? 55 times 56 divided by 4. This one and that one 14, so 70, yes? A to the power of 4, b4. Yes? And the rest of it, you don't need to calculate, yes? What is the rest? The next one is a3b5. a3b5 is 56. What is the next one? Is 70, yes? Oh, no, sorry, is 28. 28 a2b6. And what is the next one? 8 ab7. And what is the next one? b8. So it is faster if you want to do it. But that's up to you. This is not in the formula sheet. So if you want to use it, you have to have it in your memory. But that was the proof. Okay, now let us solve a little bit more interesting problems. The first thing is that, let me just tell you this. Do you remember I wrote a formula on the board for you last time, and we had a story proof for it. N choose 0, n choose 1, n choose 3, and then up to n choose n. I told you prove that this becomes equal to 2 to the n. Yes, there is a 2, sorry. We proved this one. Do you remember the story behind this proof? The number of subsets. So if I consider a set with cardinality n, let A be a set with cardinality n. The number of subsets of this set A on the one hand is this. But on the other hand, the number of subsets, I can assume that there are some subsets of this set without any elements, which is there is only one of them, the empty set, but I can imagine that I am choosing nothing from that. Or I have one element subsets, and you know that in a subset order doesn't matter, so that's a combination. Or I have 2 element subsets, 3 element subsets, or n element subsets. It is clear that if I add them up, it gives me exactly the total number of subsets. So the total number of subsets of a set of cardinality n, on the one hand is 2 to the n, on the other hand is this sum. So they have to be equal. But now you can prove this using binomial theorem. How? The formula of the binomial theorem is up there. So this is the only analytic way. If you want to write the formulas, I couldn't find any way to add the formulas. Might be, there should be. No, I don't see any at least I don't have on my mind. So that you can use the formula here, that famous formula of these numbers, to use this and sum them up to 2 to the n. But how can I use the binomial theorem to prove this analytically? Not by story proof. Let me write the formula in front of you here. What? This formula is valid for which values of A and B? It is valid for any real number, including, yes, including 0, but 0 will not give me the same. If I put 0, what do I get? Hmm?
Choose A and B to be equal, like evaluate where A and B are both equal to
1. So if I choose A to be 1 and B to be 1, the left-hand side becomes 1 plus 1 to power n. The right-hand side becomes sigma k goes from 0 to n choose k, 1 to power n minus k, 1 to power k. Yes? But of course, 1 plus 1 to power n is nothing except 2 to the n. And 1 to power n minus k is 1, 1 to power k is 1, so this is nothing except 1. So it becomes sigma n choose k, k goes from 0 to n. And if you expand this, it becomes n choose 0 plus n choose 1 plus n choose 2, and it continues until n choose n. So that's the proof. So it is sometimes usable. For example, I have written something. I'm not saying it is better to know this technique, but I'm not saying that understanding which number is suitable is always easy. For example, I have written this sum. Can you find the exact value of this sum? The sum is, let me see, 10 choose 0 minus 3, 10 choose 1 plus 3 to power 2, 10 choose 2, and then minus dot dot plus 3 to the power of 10, 10 choose 10. I want to draw your attention to this technique. Okay? They can design a lot of questions because you have to reverse engineer this. The person who designs the question, they can do whatever they want to and then expect you to do reverse engineering. But in this case, I don't think it is hard. So have this trick behind your head if you are interested to solve some of these kinds of problems. So if I ask you to solve this, of course, one way is to calculate all of them, but one way which is more efficient is to have this theorem in mind and then try to choose appropriate values for A and B and N so that the right side matches with this one and the left side will give you the answer. Okay? I'm not saying that all these types of questions can be solved using binomial theorem. That binomial theorem is one possible trick if the question is designed based on that binomial theorem. Do you see the numbers here?
1 minus 3 to the power 10.
What?
1 minus 3 to the power 10.
So it means that what you are suggesting what value for A?
1
What value for B?
minus 3.
-3. And what value for N?
10.
10. Okay, let us double check what you are saying. So you are saying that I go to this formula here. I put 1. Instead of B, I put -3. And instead of N, I put 10. And then on the right-hand side, if that is working, then the right side should be this series. So N choose K. N is 10, you said. A is what? 1 to the power of 10 minus K. And B, as you said, is -3 to the power of K. And K goes from 0 up to 10. So this is easy because it becomes -2 to the power of 10. But let us see if this really gives me this right-hand side. I think you are right. That's right. Because if I put 0, it becomes what? 10 choose 0, 1 to power 10, which is 1, -3 to power 0, which is 1. So yes, at least the first term match. The second term, I have to switch K from 0 to 1. If I put 1, it becomes 1 to power 9. By the way, don't consider this because 1 to any power is 1. So here, K is 1. So the coefficient becomes -3 to power 1. So it becomes -3 But what happens here? It becomes 10 choose 1. Yes, I think it survives. So let us go to the next one. The next one I choose k to be 2. It becomes positive 3 to power 2. And then the next one becomes 10 to 10 choose 2. And if I continue this, the last one I put 10. It becomes 10 choose 10. And this is 3 to the power of 10. Yes, that's correct. So by these choices that you introduced, the expansion of the right-hand side matches exactly with the series in the problem. So the answer to this is just minus 2 to power 10. And minus 2 to power 10 is positive 1020. Okay? So sometimes I'm just drawing your attention to this trick. I'm not saying that this is always the trick, but it sometimes works. Any questions? Okay. But another type of questions are of this type. Okay, so let us solve these types of questions and we are done. So I want to wait for you, okay? So consider the expansion of 3x minus 2y to the power of 18. Consider this expansion. What is the coefficient of x to the power of 13, y to the power of 5? Or let me do it the other way around. X to the power of 5, y to the power of 13. It doesn't matter, of course. So let us say that you are patient and extend this. Even with binomial theorem, it has 19 terms, so it's not that easy. Let us say that you expand that, and one term will be this term. It has some coefficient here. The question is not the expansion. The question is the coefficient of this particular term. It's a very standard question, and it's very simple. I want to wait for you, okay? I think this is simple, yes? So let us just do it. So you can do it faster, but what I do, I compare it with the binomial theorem formula. So I replace a with 3x, I replace b with minus 2y, and I replace n with 18. So the formula becomes equal to sigma, k goes from 0 up to n is 18. Then I have 18 choose k. Then I have a, which is 3x to the power of n minus k, and then minus 2y to the power of k. That's the general formula, yes? But then if I want to see, if I expand that, it becomes sigma, k goes from 0 to 18. 3 to power 18 minus k will serve as my coefficient, one part of the coefficient, minus 2 to the power of k will also the same. And then these are the numbers. They can all together, this becomes the coefficient of x to the power of 18 minus k, y to power k. So what I did these replacements, and then I 3 to power 18 minus k, which is a number, and minus 2 to power k, which is also a number. I took them and put them next to this coefficient, and then I have this one. But I am not interested in all of them. I am interested in this term. For this term, k should be what? If I want to have this term, this. So k has to be 5. Yes? And then this means that this is my coefficient, but k should be 5 because different values of k's will give me different terms. I am interested in the coefficient of this particular term for which I have to choose k to be 5, and that is 5. So the answer to the question is 3 to the power of 13 minus 2 to the power of 5, and 18 choose 5. That's the answer that I expect you to write down. Yes. Pardon? Oh, okay, thank you. Yes, k should be 13 because I compared them. So thank you. So k is 13. So this becomes 5. This becomes what? 13. And this also becomes 13. Thank you. And that was very simple. But let me ask you a different question. That's also a good one. So the question is this. I give you a binomial expansion, but a little bit complicated one. So the fourth root of a cubed plus 1 over the third root of a squared, and then totally to the power of 17. The question is that, is there any term in this expansion which is independent of a? Okay, if there is, find that term. What do I mean by that? For example, let us go to Math 1C. Let us say that you are in Math 1C and I ask you to calculate this. So you say the first one squared, 2 times the first one times the second one, plus the second one squared. But because of the combination that you see here, in this a and that a are cancelled, so if you simplify it, one term becomes without any a's in it. And that term is independent of a. Okay? So if I ask you, is there any independent term in the expansion of this one? Of course you say yes, and that term is 2. I am asking you the same question, but with the harder numbers and expansions. So that's the spirit. So the goal is that if someone raised this to power 17 and simplify everything, is there any term without a in it? And if yes, what that number is? So in this you might need this formula. So the nth root of x to power m, hopefully you know that this is x to power m over m.
So like a alone, like just an a.
What?
Because I mean a is still a squared is still there, right?
No, what do you mean? I'm saying that in this expansion there is a term without a. Yes, there is a term without it.
Oh.
Yes, not every term. There is a term.
There is a term that is independent of a.
What is the number? Is that friendly number?
Sort of 2 times. Wait, I mean 2 times. There are 2 terms, but they can be combined into one term. Yes. How do you like your terms? Do you want to simplify or not?
No, it is always simplified version,
Okay.
even without saying it. Yes.
2 times parentheses 17 8.
Okay, okay. So what we do, we have to do the replacements, yes? So what we do, we replace A with this one in the formula. And then we replace B with this one. And then we replace N with 70. That's what we are supposed to do, yes? Okay, so what we do now, we write the formula. So this becomes sigma, k goes from 0 to 17. 17 choose k. A, which is this one, the fourth root of a cubed to the power of 17 minus k, multiplied by b to the power of k. This is the expansion to this expression, yes? But I want to get rid of a. A is there unless the combined exponent turns out to be 0. If the exponent is 0, then a is gone and cannot be viewed. So I have to do some simplifications. So I would prefer to write it down. 17 choose k, but this one I will write it as a to the power of 3/4. What? So a to the power of 3/4 to the power of 17 minus k, and then this becomes 1 over a to the power of 2/3 to the power of k. Then I will try to simplify them, yes? Okay, so what happens, let me just do simplification here. So sigma k goes from 0 to 17, 17 choose k. Okay, so here 3 over 3 should be multiplied here, so it becomes 3 times 17 is 51 minus 3k divided by 4. And then I bring this up, it becomes negative 2/3, and I multiply it by k, so it becomes 2k over 3. But then I know that because I am multiplying them, the bases are the same, so I can write the same base, and I add the exponents. So let me write it more properly. So let me write a bigger, and these two will be the power. So this is a to this power, yes? Okay, so that is my expansion. That is not something I can do with it. But the only point is that is it possible that a cancel out? The only way that a can cancel out is that the exponent of a becomes 0. Otherwise, a will survive. So the question is that, is there any k for which 51 minus 3k over 4 minus 3k over 3 becomes 0 or not? This is the question. I have to solve it. So for example, I move this to the other side, so it becomes 51 minus 3k over 4 is equal, what was that? That is not, this is 2. Okay, so this becomes 2k over 3. Then I would say, for example, this multiplied by that 8k is equal to this multiplied by that, which is 153 minus 9k. So I move this to the other side, it becomes 17k is 153. And then if k is allowed, then the answer is positive. And if k is not allowed, the answer is negative. So k is 153 divided by 17, which I would say is 9. Is 9 acceptable? For example, let us say that k comes out to be 18. Is it acceptable? No, because k is within the range from 0 to 17. If it is bigger than 17 or negative, it is not acceptable, then the answer to question is negative. In this case, the answer is positive. But let us say the k becomes 9.1. Is it acceptable again? No, because k in this case should be an integer. So the answer is this one. But can you tell me which term? Of course, which term doesn't make sense because you can arrange them. But let us say I follow exactly the same rule in order. Which term is independent of a? The 10th term. Okay, but that is not, that the question is that, is there any term independent of a? We would say yes. And then what is that term? So what is that term? I put 9 back here. But of course, this becomes 0. So the answer finally is that yes, that term is what? 17 choose 9. What?
Because doesn't 17 choose 8? Isn't that the same?
No, I don't understand what you mean. Yes, but what did you say? A coefficient?
Yeah, I've got it a bit wrong, but if you change which of the a's are k and the other is 17 minus k, you can also get that 17 over 8 is also the same answer. So 17.
No, the answer to this is 17.9, which is always equal to 17.8.
Yeah, exactly.
So it doesn't matter. When I ask you if the is there any independent term, the answer is yes. And what that term is, if you write this, that's okay. If you write the other way around, that's also okay. Because there is a formula, and this is always the case. So it doesn't matter. Okay, so the lesson is finished here, but because we have a little bit of time, so let me ask you one more question, which is not related. We can relate it to this one as well, by the way. Okay, so let us ask you this question. So do you remember we had this, we just had this formula now. So if I ask you what is let me write 99, 0, plus 99, 1, plus 99, 2, plus 99, 3, and then you continue until 99, 99. So if I ask you what this number is, what is the number? Yes? 2 to the 99. Yes, we did it in two ways. One by storytelling and one by the binomial theorem. But now let me ask you this question. What do you think this will be? So I'm not considering the odd ones. I'm considering only the even ones. What is your guess for this? Of course, if you can answer this question, you can also know what happens if I have the odd ones. Because I have the totality, if I know what is the sum of the even ones, you subtract it, you will get the sum of the odd ones as well. You have some clue, yes? If I want to use the binomial theorem, what value you choose for n? Yes? 99. N is 99. Okay, do you have?
Yeah, I have different answers.
Yes?
2 to the power of 50.
No, but I think your thinking is correct. Your calculation is wrong. You are dividing something by 2? No, okay. So 2 to the power.
Yes, I am. Oh, wait, is it 2 to the 4th 9?
No, come on, Simon. 2 to the power of 99 divided by 2 becomes 2 to the power 50.
No, that's not what I'm doing.
Oh, you are not doing this.
I'm doing a different way.
Okay, but the answer is not that. It is 2 to the power 98. The answer is that. Yes. So this number is half of this number. But why? Yes.
Because, like, if you work backwards, they should be the same. Like 99 chooses 0 is the same as 99 over 99, but that is not true. So you have only half of it.
What did you say? No. Is it?
Yeah, wait.
Yeah, because 99 choose 0 is the same as 99 choose 99. So if you check all the terms,
Half of them are gone.
From-
Same half.
yeah.
So you are saying that I can I can take that one and write this one. Yes? And then I can take the previous one and I write, what is the previous one? It's 98, yes? I can write this one. Yes, that works. Yes? Okay, that works. But it's a very good way of doing it, by the way. So you are splitting into two, and then you are using that formula for all the terms, yes? And then hopefully, are you convinced how many terms are there? One term will survive in the middle, yes? Because, no, exactly, we have 100 terms. So we can divide them to two groups. But one way to look at the problem is to use the binomial theorem, and this is always valid, to the power of n sigma, and I want to draw your attention to this. Sometimes this is also good to know. Okay, so here in this case, let me write 99. And then the interesting thing I want to do, I want to choose A to be 1 and B to be minus 1. Okay, then what happens? The left-hand side becomes 0. Okay, K goes from 0 to 99. So the right-hand side becomes what? I don't need to consider A because A is 1. So I only consider sigma. K goes from 0 to 99. 99 choose K, and then I have B to power K. If I expand this, so by the way, B is minus 1. So if I expand this, the first one becomes 99 choose 0. Then I put 1, it becomes negative 1. So it becomes minus 99, 1. And the next one becomes what? 99, 2. And the next one becomes 99, 3. And then you can continue until I put 99, it gives me the last term with negative sign. But the previous one is with the positive sign. 99, 98. Yes? So I know that this sum is equal to 0. Yes? So it means that the sum of the even ones is equal to the sum of the odd ones. Yes? Because the sum of all of them is 0. The odd ones come with negative sign, the even ones come with positive sign, and the sum is 0. So take the negative ones and move them to the other side, they also become positive. So the sum of the terms with the odd numbers in the bottom is equal to the sum of the numbers with even numbers in the bottom. Yes? Is that clear? Interestingly, can you come up with a story for it? Why this number should be equal to this number? If you want to tell a story, that's also interesting. Yes.
Okay, well, the story then, I mean, I guess, well, you want to split for the left and right side individually or connect to one story, which does both of them at the same time.
Yeah, if you want to say that story, it works. So what does it mean? It means that if I have a set with cardinality 99, the total number of subsets with even number of elements with them is equal to the total number of subsets with odd number of elements within them. Yes? But it wasn't trivial from the beginning. I don't think it's that trivial, yes? For one case, it is trivial. Now, because we know the formula, don't force it to work. I mean, you should have a logic behind that. So 99 is a big number, so let me make it a smaller, okay? So what we are telling, let us write A, B, C, and D, and E, 5 elements. Is it obvious that the number of subsets with odd elements within them is equal to the number of subsets with even number of elements within them.
Yeah. Because it's 5 choose 3 and 5 choose 2, which should be.
No, the total number of odd ones. No, I mean, for some people, it seems obvious, but to me, it's not obvious. It needs a reason.
Because, I mean, if you do.
No, the answer is yes.
Yeah, well, yes.
The answer is yes because of this kind of properties.
But if you choose, for example, if you choose for the odd ones, then it's 5 choose 1, and then 5 choose 3, and then 5 choose 5. And those should all be equal to 5 choose 0, 5 choose 2.
No, but you are repeating the same argument as Hafsha said for 99. Yes, of course that works. But is there any other way to convince yourself that the total number of... So for example, let me write a bag, take a bag. What I will write here, for example, I would write here A, it is a subset with one element. I can write a subset with 3 elements. Yes, there are many of them. I can write a subset with 5 elements. Yes? So 5 elements. And then there are many of them. On the other bag, I write all subsets with even elements, even number of elements. For example, I don't know, A, B. I can write B, C, D, E. My question is that if someone is patient and write all these kinds of these subsets and count them, and then another person writes these subsets and count them, why the number of elements in this bag and that bag should be the same without even doing any other kind of this very complicated stuff? Yes?
I guess there should be a one-to-one correspondence.
It's a one-to-one correspondence established immediately, yes? Because, for example, but there is a small point in it. So, for example, which one do you connect this one? To which one of them?
The ones
Without A.
next to E.
Yes. So I mean that the one without A is there. So you have what? You have B, C, D, and E. So you connect them together. And which one this one is connected to? C and D. So you see that there is a one-to-one correspondence between these elements and those elements, so the number of these should be the same. Yes? But it doesn't work. This works here because I chose 5 elements from the beginning. If I choose 6 elements from the beginning, how do you do that then? So everyone agrees, without even knowing the number, I am convinced the total number of items here and the total number of items there are equal. But let us say that from the beginning I have A, B, C, D, E, and F. How can I establish the one-to-one correspondence now? That is harder. Because this method doesn't work, do you agree? If I have odd elements and then I take them off from there, still odd elements are left. So understanding this from this perspective is harder, but that's also possible. So I want you to think about it yourself. But anyway, formally at this step, at this stage, this combinatorics is finished. Okay? And then from next lesson, I think it is good to have a quiz. That was a long chapter. We had a quiz on set theory, but we didn't have any quizzes on combinatorics. So I will think about it and put it on a school stuff so that you can know when the quiz will be. Might be that's a good idea to break this into 2 quizzes as well, because it was a very long chapter. Okay, I will let you know. Okay, but finally this chapter is finished. Next time, our next lesson will be differential equations. And differential equations is very similar to Math 4 rather than Math 5. Any questions? Thank you.